Hello, everybody. I'm Joshua Hibbard. I'm a student at University of Colorado Boulder. My advisor is Jack Burns. And for just 15 minutes, I'm going to ask you to put axions out of your mind for a moment and float through the cosmos and 21 centimeter cosmology with me. And also, being an astronomer, I'm going to inflict as many photos from telescopes upon you as I can. To give a brief overview of what I'm going to talk about, I want to first give a history of the universe, like a good astronomer, and I'm going to then show you why we can use what is called the 21 centimeter cosmological signal to map the earliest parts of the universe. And then once we have done that, we can use it to put constraints upon dark matter, specifically in the context of structure formation and, in this case, warm dark matter. Very, brilliantly named. And once we've gone over the constraints that we can put using the 21 centimeter signal, I'm then going to show you some of the upcoming lunar telescopes that will be launching in the next 5 years to measure this signal. Okay, so first off, the evolution of the universe. We start off with the Big Bang, of course, and recombination at a redshift of about 1100. And then the farthest that has been probed to date by mostly space-based telescopes is about a redshift of 7 or so. I think that's the 7.4 is the current limit from the highest detected quasar. But there's this interesting part of the universe where there is absolutely no data currently, and that is what we currently want to target with 21 centimeter cosmology. So if you imagine right after recombination, the universe is filled with neutral hydrogen gas, or intergalactic medium, astronomers call it, the IGM, and it's doing nothing during this time but slowly falling into gravitational halos and just cooling adiabatically as the universe expands. And then eventually around, of course, uncertain redshift of 15 or 30, somewhere in that range, these overdensities get so large that you get the baryons collapsing into stars and galaxies, and then these stars and galaxies start emitting light. And that light changes the kinetic, the thermal history of the neutral IGM. And once that has continued in earnest, you're releasing UV photons, you then ionize the IGM and lead to at about a redshift of 7 to 5 reionization, which is of course kind of a dumb name because it's the first time it's been ionized. But in any case, we want to know then, during these unmeasured epochs, what is happening to the IGM. So we're going to use the 21 centimeter line of neutral hydrogen to map this. So you just have a diagram here of the proton and the electron in the hydrogen atom, and when the spin of the electron is anti-aligned, it gives off this light with the characteristic 21 centimeter wavelength. So the signal itself is essentially just a quantification of the number of hydrogen atoms in the aligned state versus the unaligned state, and that's what the spin temperature is quantifying. And so you can imagine at every single point in cosmic time, there is some amount of spin temperature signal that is being emitted. It's emitted and then it's redshifted down into the radio frequency regimes by the Hubble expansion. And so what you're actually going to see if you map this signal over the whole sky, that is to say the monopole component, is a frequency spectrum that doesn't correspond to, say, like what you might think of as a spectra, but actually corresponds to cosmic time. So what we're actually going to be measuring in this case, though, isn't just the spin temperature, but the differential brightness. And so you imagine the universe filled with neutral hydrogen, and you have the CMB as a backlight. And the way that the CMB interacts with this neutral hydrogen cloud produces the 21 centimeter signal, because the spin up and spin down states are going to be sensitive to things like collisions and the radiation background. And so this differential brightness temperature, as I was saying, is sensitive to the radiation background, the amount of neutral hydrogen, because obviously once it's ionized, the signal will disappear. So this is what, broadly speaking, a sort of typical 21 centimeter spectrum is going to look like. So this first trough, the dark ages, is going to occur because the gas is coupled to the spin temperature is coupled to the gas temperature because the universe is very dense. And what you see then is that the gas cools more fast than the radiation background because the radiation scales with 1 scale factor and kinetic temperature with 2. And so you see that the signal should appear in an absorption trough. What's exciting about this trough in particular is that there's no messy astrophysics. It's all pure cosmology. So if we measured in this spectrum and saw anything different from lambda CDM, it would be a big deal. It'd tell us a lot about dark matter. But keep in mind where this is at in the spectrum. This is going to become a problem later. It's less than 50 megahertz. Okay, so then the second trough occurs when the first sources turn on, Lyman alpha photons are released, and through the Waldhausen field effect, it couples the kinetic temperature of the gas back to the spin. And so what you get then is the gas is changing differentially to the CMB again, and you see another absorption trough. Then at the bottom of the trough, these first stars and galaxies collapse into compact objects, accrete matter like black holes do, and release X-rays, which heats the gas once more and can even push the signal into emission above the CMB temperature. And then, of course, by the end, reionization, you have reionizing photons that are destroying the neutral hydrogen, and eventually the signal disappears. So that's the theory in general, and that's what we want to measure. And as I was saying, it'll tell us about cosmology as well as the first astrophysical sources. So the three primary challenges, though, to observing this signal are first, bright foregrounds produced from galactic synchrotron radiation, which, as you can see, is something like 4 to 6 orders of magnitude larger, which is a very big problem. The second is that the radio antennas we want to employ to measure this have to measure a large bandwidth, and because of that, the structure of the antenna beam, the directivity, changes across the band, and you end up like coupling spectral sources with spatial features of the galaxy. So that's a problem. And then the third biggest one, as you can see here, we're in low frequency radio, and 98, 95 is the FM band. So you have a ton of radio frequency interference. The ionosphere starts to be a problem, and below 40 megahertz is completely opaque, so you can't even actually measure the dark ages trough from the Earth. And then vegetation, changing soil properties, all of these things can swamp out the signal by themselves. And one way, though, to potentially solve these environmental effects is to put a telescope on the moon. Sounds very sci-fi, but I'll show you at the end that it's happening. So, and the other thing you can use actually is the difference in the anisotropic foreground to try and separate it from the monopole component, which should be the signal. Okay, so why do we care about the signal, and what is it going to tell us about dark matter? So in the standard cosmological paradigm, we have cold dark matter, where you have a low relic velocity at decoupling, and you get lots and lots of small halos, as you can see here in this N-body simulation. So you get lots of small dark matter halos, which get lots and lots of little galaxies. And those lots and lots of little galaxies are going to emit a lot of light and change the IGM. If you parameterize those, so there's no interactions with baryons, this is just the thermal relic velocity of dark matter. If you just slightly decrease its mass so that it moves faster, then the smallest halos are going to diffuse out, and you will not get these dwarf galaxies collapsing. And so that's what you see in the case of the middle one, sorry, this should be over here, the warm dark matter, where you get the smallest halos having diffused. So we're going to parameterize this level of structure formation just with the warm dark matter mass m of x. And warm dark matter is essentially defined to lie in the range between where you still keep large-scale linear structure formation, but you get a little bit of diffusion of dwarf galaxies. And the constraints on that are in the KeV range. So the Lyman alpha forest constrains it to be greater than about 2 or 3, and once you're larger than like 10 to 12 keV, you just approach CDM for all intents and purposes, observationally. You won't be able to detect anything beyond that. And the motivations, of course, for warm dark matter are related to problems that have recently emerged in the apparent lack of small-scale structure predicted by lambda CDM simulations. So things like missing satellites. The Milky Way should have like on the order of 100. There's only a dozen. Of course, they find more all the time, so I understand this is tentative. Also, the too big to fail problem, named in 2008, of course, where you have large halos that should have collapsed with galaxies, and we don't observe galaxies in them as well. Lack of structure between filaments. Possibly some people think the core cusp problem for this is related. And an elegant way really to kind of solve all of these small scale things is to just make dark matter warm and then diffuse all of the smallest halos. And of course, baryonic processes, feedback supernova in the smallest halos could also be responsible for this. They could blow up the galaxies before, but we would still expect to observe some, of course. But anyway, so I hope I've convinced you then that the number of dark matter halos is a very important ingredient to measuring structure formation and thus to measuring the global signal. Because if you have more halos, so more small ones, they're going to emit more light and they're going to change that cosmic dawn trough that I was showing you earlier. And so if we can measure the signal in this way, it's a great way to test dark matter in an epoch that should be really sensitive to the nature of dark matter, the mass in this case. So, but the big question, right, is can we separate the cosmological parameters from all of the unknown astrophysics that we have to dump into the cosmic dawn? And that's essentially what the work we were doing. So first what you have to do, of course, is put dark matter into your simulations, warm dark matter. This is just the number of halos of a given mass. So you can see at the low mass end here, there is a cutoff imposed by dark matter, the dotted and dashed, whereas there's no such cutoff in CDM. So you put in your number of halos then, you put in, then we need models for star formation. So in this case, we're just going to assume that all dark matter halos that we have in our simulation host star formation, and then we need to parameterize how much light they have, how many photons in each band, and how many of those escape from their halos. So we wanted to be as exhaustive as possible in this and try several different star formation models and star formation efficiency. So in the simplest case, you can imagine that all you need is that the star formation rate is proportional to the amount of matter that's locked in dark matter halos. It's pretty simplistic, and a better one that you can do is have it be dependent upon the mass, which could characterize feedback processes for low versus high halo masses. Then we can add in another parameter that should be degenerate. So we're pretty sure there should be POP3 stars, the first generation that would have formed in low metallicity environments. They're going to be much larger than POP2, and they're going to be much more explosive and die on shorter time scales. And because they could exist before the POP2 stars, they would put in light earlier into the signal. So they could appear just like what warm dark matter does, which is shifted. So, and then we want to introduce a phenomenological model as well, so that we can be certain that if we need to, these parameters can help us see if we're modeling all the relevant processes. So here's what some of the signals look like when you change the dark matter parameter. As I was saying, if you go towards CDM, the signal is earlier because you have more and more halos, so more light. As you increase it, the warm dark matter mass, decrease, then you get less halos and the signal's delayed. And here's what some of the POP3 star effects do. They can actually create these sort of asymmetric features in it. So you put all of the models together, we run it through a Fisher forecast to get the model degeneracy, the parameters, which is of course a Gaussian approximation to them. And the answer is yes, we can still actually say something about what the warm dark matter mass is, even including all of these different models with different star formation parameters for POP3 and between the two different star formation models themselves, which is exciting. So essentially, the global signal appears to be a great way to be able to constrain dark matter, even in the presence of lots of unknown astrophysics. Okay, so really briefly now, let's talk about why going to the moon is so great and what's happening in this case. So the NASA CLIPS program, Commercial Lunar Payload System, has 2 radio telescopes currently funded to go to the moon to start making these measurements. The first is ROLS's, the Radio Wave Observations of the Lunar Surface of the Photoelectron Sheath. Yeah, the NASA tortured acronyms are their thing. And it's going to have 4 cross-dipole antennas. It's going to be landing on a near-side surface in this Mare Crisium, the Sea of Crises. You can see sort of its topological elevation map here. And the goals of this particular experiment are really to characterize lunar systematics. We need to know what they are so that we can continue to improve our systematic modeling for, a signal that once again is still 6 orders of magnitude lower than the foreground. So we're going to do, the things we're most interested in, of course, are measuring the foreground below 30 megahertz, which has never been done, measuring the local EM environment and the reflection of radio waves in this case. Okay, now the one that's a little more close to what we actually want to do for measuring this signal is the Lucy experiment, which is the second one. Oh, I should mention the ROLS's is launching earlier next year. Lucy is spearheaded by a team at Berkeley, and this telescope is going to be put actually on the far side of the moon. and it is hopefully launching in 2025. They're both funded missions, I should mention. Lucy is split into two, light and night. The one that we want, of course, is the night mission, where it's going to go on the lunar far side, and it will turn off as it makes these measurements. And it has batteries to keep it alive through the 14-day lunar night and make, hopefully, the best measurements that you could in this spectrum without any locally generated EMI. And of course, because we're on the far side, right, we're shielded from all the radio frequency interference from Earth, which is what makes it also so desirable. So this is the schematics and the design pattern. It'll have these 4 antennas whose length and bandwidth is still an ongoing scientific determination. I'm an astronomer and also a theorist at that, so I'm afraid that I don't really know anything about this except that it's not hydrogen and not helium, so it's a metal. It's metal. That's all I know. And here are some of the regions that we're looking into on the far side to put it. We don't want to put it in a crater, but we do want to put it somewhere that has low slopes and a lot of access to the sky. So yeah, in summary, I hope I've convinced you the 21 centimeter signal is great, not for just studying the whole evolution of the early universe, but for constraining dark matter, and that there are 2 lunar telescopes that are going in the next 5 years to start making these measurements. Thank you.
Thanks so much. Fascinating. What's wrong with putting the system in a crater?
In the crater, the problem I think is people are scared of trying to get these to land there without them impacting on the sides of basins, or also you get less sky coverage because if you're down in the crater, the rims of the walls are more difficult to model for radio frequency interference. And apparently there's something too about the soil. I'm not a lunar geologist, but these people tell me that the soil isn't as well mixed or something, so the dielectric constants are wonky, and it's much harder to measure what reflection is going to be from the surface. And of course there's not going to be any ground planes, so you have to be able to measure that, because we are not going to be able to put a 50 by 50 meter ground plane on the moon yet. Stay tuned for the 2030s.
For the question right there.
Hi, nice talk. I wonder if you can comment a bit about the results coming from JWST about these really high redshift, very bright galaxies, whether this puts pressure on warm dark matter in general, or the models that you're using for star formation.
Yeah. No, it's really exciting. So the problem is that JWST will probably not see the first stars, and JWST will only see the brightest of these. So its picture of star formation is going to be very incomplete. If you want to look in, I think it's Furlanetto 2017, they do projections, and at the highest survey level for JWST, they will probably only see 10% of the star formation at redshift of 15. But it will still help to constrain something like this plot, which is the UV luminosity functions. JWST is going to push it out to something like this level, and you can already use it to constrain warm dark matter, because you can see it already really sort of disfavors the 2 keV, just like the Lyman alpha forest measurements.
Yeah, just a super quick question. The lunar, the frequency range for the lunar module,
yeah,
is it going to be all the way down to basically the frequencies at which 21 centimeters coupled to the CMB? Is that how I should think of it? Sorry,
down to what?
Down to the frequency where the 21 centimeter signal is coupled to the CMB, early at the highest redshifts?
Well, so the 21 centimeter signal is always a backlight against the CMB, but you mean coupled to it, because if it's ever actually coupled to it, it's 0.
Yeah, exactly. I mean, when the differential temperature is 0, I think it starts being non-zero at what, a redshift to 200 or something like that?
Oh, you mean before? Oh, yeah. So before the Dark Ages trough has finished. Yeah. No, it won't be. It will not be able to go down that low.
Oh, it won't be able to go all the way down to that beginning.
Yeah, but I, as far as I'm aware, that the community is not as interested in that part of the 21 centimeter spectrum, because it will be essentially 0.
No, I mean, I want to know if it's going to go all the way down to where it starts being down to basically the beginning of the signal.
Oh, to the Dark Ages trough.
Yeah.
Oh, maybe 10 megahertz is kind of where for Lucy. Rolls's will go down to actually 100 kilohertz, but
okay.
Yeah.
Interesting. Yeah. Thank you.
Thank you for the great talk. Have you considered any constraints on cold dark matter and maybe WIMPs or Axions?
Yeah. So you can do, as many people here know, like structure formation in these models, and they also produce cutoffs in like the nonlinear power spectrum. And unfortunately, a lot of those effects are very degenerate, but depending on how you parameterize, say, the transfer function from like the linear to the nonlinear, you can like create up a parameter space that will like discriminate between the different models. But yeah, essentially all you're doing is parametrizing structure formation in the same way with axions. Of course, in all these cases too, they're not including, say, a coupling term to baryons, which you would if we're doing the GA gamma gamma stuff. And as far as I'm aware, that's not something people have done yet.
Hi, thank you for the great talk. With Lucy Night, which is going to be on the dark side, what are the main sources of radio frequency interference? Like all of the terrestrial ones are blocked. So what do people think the main noise sources will be?
The main noise source is still going to be the galaxy. The galaxy below 40 megahertz is like 10,000 to 100,000 Kelvin, and the signal's like millikelvin. So it'll be the dominant noise source. Yeah. Also Jupiter, actually. Jupiter's very bright in low radio frequency ranges.
Well, there's one last question here.
Just going on for the JWST comment, I think one of the most interesting things there is that they're finding nonlinear galaxy-sized objects at redshifts of 10 plus. So that's going to limit straight away the power on short scale. So I think that's a significant concern for the warm dark matter picture in general, actually.
Yeah.